So now we'll be discussing the idea of potentiometers, and depending on the textbook you are using, you might also see this being referred to as a slide wire potentiometer at times. And again, the basic idea of a potentiometer is to supply a continuously variable voltage, right? So it provides a variable voltage which we can change basically, and as the name shows, by changing the length of wire which is being used. So the idea here is this, that we know that the resistance, the voltage dropped, right, the potential difference across any certain material is proportional to the resistance, right? This is the idea that we also used in the potential dividers video. And then we also know by that equation R equals rho L upon A that R is proportional to length. So putting both of these together, what we get is that the voltage across any conductor is proportional to its length. This is the basic principle which is underlying the principle of how potentiometers are used. The circuit symbol for potentiometers, which is going to be used in your syllabus, is like this. So this is how you have that basic resistor shape, and to show that it is changing with voltage, and again basically how it's changing is based off the length. So this is some sort of a movable contact along the length of the wire. So this is how the circuit symbol for a potentiometer looks like. What is actually happening is something like this. And between so this is a basic circuit, and again just based off this you can also have a internal resistance here, right? You also have questions related to this in your paper. Let's close this in a box to show that this is the entire model of the cell itself. And then you can have some sort of resistance wire which is connected, so something like this. And to see how this voltage will change with different lengths along the block, so for that purpose we've connected a voltmeter. If we zoom into this, so if we go ahead and say that this entire length of wire which is used here, so if all of this is some length L, right, so this is the length of wire used, if this is L, and if the length of wire across which we are having a look at the potential differences, this is X. Let us also define two more points. So the left end of the wire is called X and the rightmost end is called Y. Now if you remember anything from the previous videos, you'll know that if the EMF of the cell is E, and if the internal resistance is small r, then we know that across this end we would have the terminal voltage Vt, which is equal to E minus IR appearing, right? So this is like a prerequisite from the earlier videos. So then after having talked about this, we can just use the direct proportionality between length and voltage that we just talked about. So if we say that this Vt, or whatever voltage this is, if we ignore this for right now, if we say that some voltage xy appears across this entire length of wire, then we can say that a proportional amount of voltage would appear across this fraction of the length. So then I can just go ahead and say that the voltage across this length, right, so across this length x, it would just be that fraction of the length, right? So this length as a fraction of the total length multiplied by the total voltage appearing across the xy ends. So if we look at this equation, we can say that if the contact is placed at point X, then there would be no voltmeter reading because there is no length, so there is no potential drop across this, so there is going to be no voltmeter reading. And as this is moved continuously. So because the length is increasing, the resistance would be increasing, and hence the voltmeter reading would also be constantly increasing. And then as we reach y, then all of this voltage would be appearing on the voltmeter, right? So we can then also go ahead and say that Vx is 0, right? So actually let's say if the contact is at x, so V is 0, and if the contact is, actually let's make this uppercase X. So if the contact is at X, V is 0. If the contact is at Y, then the entire voltage that Vxy appears, right? And if we talk about how it's changing, so we can say that the voltmeter reading steadily increases from X to Y. From X to Y. So this is like the basic idea of a potentiometer, but the more challenging questions that you will see will be in the context of something we call null methods. So how can we use a potentiometer to figure out an unknown EMF? Right, so finding out an unknown EMF using a potentiometer. This is what the majority of questions related to potentiometers are on in your exams. And for finding this unknown EMF, you need to have a known EMF. So what we do in that case is that we have a circuit diagram like this. So the circuit diagram looks something like this. So this is some known EMF. Some books might also refer to this as a driver EMF. Again, it means the same thing. After this, you have just a normal circuit. But here you have that uniform wire, which we use as a resistance, just as we described above. So this is our resistance wire like this. Right, this is that resistance wire. And then what we have in the lower part of the circuit is another EMF source. Like this. And connected to this, we have something called a galvanometer. This is the circuit symbol for this. Again, this is exactly like an ammeter, but the difference is that this is used for the detection of very small currents. And here we are concerned with this fact that does this instrument show any deflection or not? Because if it does not show any deflection, then what this means is that there is no current flowing in this. Right, so this is called a driver or the known EMF. Right, let's call this one E1, and this is the unknown EMF, which is what we want to find out. So let's call this one E2. This is a galvanometer, and this is that sliding contact of the potentiometer. And then we know, based off our discussions just now, that you can use you can move the contact along here, and basically because the length would be changing, the resistance according to that wire, according to that length, would also be changing, and so would the potential difference across that length of wire. So if we do the same things as we did above, let's call this end A, let's call this one where the contact is B, and then let's call the rightmost end of the wire as C. So what we know here is the driver or this known EMF. So let's say this is some value like maybe 12 volts. Again, you know that you can also have the internal resistance here, right? If there would be current flowing here, then the voltage appearing here would be smaller. So what would happen is, we know that this is the positive end, this is the negative end. If we just use the concepts of potential, because remember the EMF is 12 volts, so I can say that the positive end, for example, is at 12 volts, and because the difference between the positive and negative terminals is 12, then I can accordingly say that this one is 0 volt, right? So the negative end is at 0 volt, the positive one is at 12 volt. Again, you can also take something like 24 and 12, or like 16 and 4, but this is by far the easiest one to work with. So we know what would happen is that this EMF source would start supplying some current into the circuit, I. Then this would be splitting up into these two currents in each of these loops respectively, right? So this current would be splitting into this current flowing through the resistance wire and into this loop of the circuit. So because of this current which is flowing into the lower part of the loop, there is going to be some reading which is registered on the galvanometer here, right? So this current which is flowing in would also need a path to flow back out. So this is where the current would flow out from. Now what actually determines how much this current is? So we know that if the contact is here, then there is going to be some some potential difference across the ends AB, which is not going to be 12. If you remember the discussion we just had, then the 12 volt would be appearing across this entire wire. So based off whatever this length is, which we called X above, there would be some potential difference across this end, right? And then if you think about it, from the lower part of the circuit, there's also this E2, the EMF of this unknown cell, which is going to be appearing across this. So that difference between VAB and E2 is what is causing the current to flow in this part, right? This is what is causing a reading to be registered on the galvanometer and for it to deflect on either side. Also, another assumption, and not really even an assumption, it's more of a requirement of this method, is that this driver voltage always needs to be larger than this unknown voltage we are trying to find for this method to work. So we know that if this length AB is very small, so if the contact is at a position like this, so we know that from the known EMF we would have a very small potential difference across this end, right? So this potential would be smaller as compared to this potential. So the current would flow from this unknown EMF to here, right? So the galvanometer would deflect a certain way. So we know that if the length AB is small, then the voltage VAB would be smaller than this unknown EMF E2, which would cause the current to flow from this bottom part into the resistance wire. So the current would flow from E2, right? So it flows from E2 into the resistance wire. And likewise, if we know, if there's a situation like this where the contact is much farther out towards C, so we know that this voltage would be larger than E2, then the current would be flowing like this through the contact into this part, right? Again, just based off the idea of potential differences, because if you remember the current of electricity chapter, the theory which was studied there, so the potential difference is what causes current to flow, right? So if the length is small, so the voltage across AB is so if the length is large, actually, then the voltage across AB would be greater than E2, so current would now flow into E2. So then if at a certain at smaller lengths, if the current is flowing from E2, and if at larger ones it's flowing into E2, so then there must be also some sort of a sweet spot in the middle where no current flows, and in that case the galvanometer would show no deflection. So then we can say this as well, that at the balance point, right, at that sweet spot of the sliding contact, so at the balance point, the voltage across AB would be equal to the unknown EMF as well, right? And then the galvanometer would show no deflection, right? Because there is no current which is then flowing into the lower part of the circuit, and all of the current which is there only flows in the major part, right? So when there is no more potential difference between this and this, then there's no current which is flowing here. All the current which is produced by E1 just flows all throughout the resistance wire, right? There's no current flowing in this part, so the galvanometer shows no reading. So again, as discussed above, we can find the voltage AB using that ratio of lengths. So that would be that length AB divided by the entire length AC times the EMF of the driver cell, which was E1. So this is how we can go ahead and find VAB, and again that would just be equal to the EMF of that unknown cell. Now something else about this method which is very, very important. So as I was just talking about moments ago, you need to have these conditions fulfilled in order for this null method to work. By the way, this is called determination of EMF by null methods, because the galvanometer shows no deflection at the balance point, right? It shows no reading. So the conditions are these, that as we discussed previously as well, that the driver EMF, that unknown EMF, must be greater than E2. And the reason for this is very, very simple, that if this EMF is smaller than this one, so even if we use the full length, then the current would always be flowing from the larger EMF to the lower EMF cell, and then we could never have the balance point even if we move the contact all the way out towards the right. And then another thing which has been assessed in some of the MCQs is that the ends must be connected so that these are positive, right? So both of these must be opposing each other. If these are connected so that the positive is connected to the negative, then the problem is that it would become a case of EMF sources in series. So both of these would be helping each other and making the current flow in the same direction throughout the circuit, right? And then no matter what you do, again you would have current flowing in this part, and you will never be able to achieve that zero reading on the galvanometer, right? So the first one is that E1 is supposed to be greater than E2, and then the second condition is that both sources must be connected as positive and similarly negative. So the positive end must match up with the other positive end, and the negative ends must then accordingly also match up, so that both of these EMF sources oppose each other, so that the balance point is obtained then. So how would this differ if, for example, if we take a practical EMF source, so that each of these EMFs has some internal resistance? So we talked about the internal resistance of this one above. So if this has some internal resistance, then this voltage which would be appearing across this would not be 12, it would be some value less than 12. So if we have some internal resistance for E1, it would affect the balance length. But now here's the important part, that even if you do have a practical EMF source for E2 where you have an internal resistance, that would not affect the balance point. Because remember that if we are talking about a null method, and this is when balance is obtained, there is no current which is flowing throughout this part, right? And if you remember that equation for the terminal voltage, so that is E minus IR. So there is only going to be a drop across the internal resistance when there is a current flowing. When there is no current flowing, then there would be no potential drop, right? So still you would have this, whatever this voltage is, VAB versus E2, right? Because at the balance point, there would be no current which is flowing in this part of the circuit. So the internal resistance of E1 will affect the balance point, right? That length at which we know that no current would flow in the galvanometer, but the internal resistance of E2 will not, right? And a one-liner reason for why the internal resistance of E2 will not affect the balance point is that there is no current flowing in that part. Will not, right? So this is something about the theory of potentiometers. Now we'll be having a look at the examples.